So we are on page 4 and we're starting the section on conversions. The way that this section works, there are a lot of different ways we can use stoichiometry and the conversions. I have them broken down by type. Once the chemical equation is balanced and the mole ratio is established, we can relate two substances using moles. The mole is the most important measure of the amount of the substance. We can relate moles with various quantities, as we've learned in previous units. It relates to mass for specific compounds. You could relate it with the number of representative particles, whether that's atoms, molecules, formula units, ions, and so on. And it could be the volume of a gas, which we've talked about so far only at STP. So we'll talk about each of these, some more than others. The first type is what I call mole-to-mole calculations. These are the most basic stoichiometry calculations. So let's start with the Haber process. We've already balanced the equation, so we'll just go ahead and write it down. It's good to have it written on the same page just for reference. I don't really like flipping from page 4 to page 2 or whatever the case is. I like to be able to see it on the same page, just a personal preference. So here's the question: how many moles of ammonia can be produced from 2.5 moles of nitrogen? Here's what we want to know. How much of this can I make when I'm starting here? I know how much nitrogen I have. How much product can I make? This is almost like I have 3 cups of sugar. How many cookies can I make from this recipe? That's really the type of question we're looking at here. And so when we're trying to figure this out, we're going to start with the value that we're given. So I know that I have 2.50 moles of nitrogen. And that's really the only thing I know right now. The question is, how much product am I going to make? This is a dimensional analysis question, and we want to relate nitrogen with ammonia. This is where we use the mole ratio. So we want to compare moles of nitrogen being on bottom so that it cancels. We want to compare that with moles of ammonia. Now, this is not the completed mole ratio. We need to put in the numbers. So for moles of nitrogen, the coefficient really is 1. And so that's 1 mole of nitrogen. And with this amount of nitrogen, I can make 2 moles of ammonia. So I'm going to put 2 here. Most of the numbers in this section are fairly easy. You could do it without a calculator. Basically 2.5 times 2 with significant figures, 5.00 moles of NH3. Significant figures are something we haven't talked about in a while, but this is where they become important again. Another question: how many moles of hydrogen are required to react with 2.5 moles of nitrogen? So now we're comparing these two things. I know how much nitrogen I have, and I know how much ammonia I can make from it. Now I need to know how much hydrogen do I need. On my cookie recipe, I said that I know I have 3 cups of sugar. How many cookies can I make? Well, now I have to figure out how much butter do I need to make that amount of cookies with 3 cups of sugar. And so we're just relating different quantities here. So with 2.50 moles of nitrogen, we want to compare how much nitrogen we have with how many moles of hydrogen. Again, these numbers in the mole ratio come from the balanced equation. It is 1 for nitrogen, it's 3 for hydrogen. 2.5 times 3, 7.50 moles of hydrogen. This last one is a different type of question. Here I'm looking at, I know the amount of product. I know how much of this I made. Now I want to know how much nitrogen went into making it. There's really nothing different about this calculation. All of these calculations work exactly the same, whether we're looking at a reactant to product, or in this case, a product to a reactant. We're starting with the number that we know. And we are comparing moles of ammonia with moles of nitrogen. And now we have to fill in our numbers. For ammonia, it's 2. For nitrogen, it's 1. So we have 1.00 moles divided by 2, 0.500 moles of nitrogen. Next, looking at the decomposition of water. Two waters breaks down into 2 hydrogen gas and 1 oxygen gas. So in this reaction, how many moles of water are consumed? So how much reactant does it take to produce 5 moles of hydrogen gas? Start with the number we know, 5 moles of hydrogen. And we want to know how many moles of water, so we are comparing moles of hydrogen with moles of water. In this case, for every 2 moles of water, there are 2 moles of hydrogen, and it tells me that 5 moles of water are consumed in this particular reaction. Next up, how many moles of water are consumed? How much reactant was required to produce 1.33 moles of oxygen gas? And this number, this moles of oxygen gas, is our starting point. Moles of oxygen will go on the bottom of the mole ratio, and moles of water will go on top. Using the coefficients, 1 oxygen and 2 waters, .66 moles of water are consumed in this reaction. How many moles of hydrogen are produced in a reaction that consumes 12.1 moles of water? Here's my starting point, 12.1 moles. We want to relate moles of water with moles of hydrogen. In this case, the coefficients are both 2. And so it is 12.1 moles of hydrogen. Now you'll notice here I've been putting the numbers every time with units, which is normal for us, but I've always been putting in the chemical, because in each of these I had 3 chemicals involved in this reaction. I had 3 different chemicals involved in the next reaction, and we need to make sure that we know which ingredient we're talking about. Because think about the cookies again. If you're adding 3 cups of sugar, you need to say it's sugar. You can't just say add 3 cups, because somebody might look at your recipe and think you're talking about the salt. If you add 3 cups of salt to cookies, they're not going to be cookies. They're going to be just blocks of salt. And so we need to specify what this is. What chemical are we talking about? Still talking about mole to mole reactions. The synthesis of iron 3 oxide, formation of rust. We've already balanced this equation, so I'm just going to write it down. How many moles of iron 3 oxide can be produced from 4.32 moles of iron? So 4.32 moles of iron is my starting point. I know how much reactant I have, and I'm trying to figure out how much product we're going to have at the end. So the mole ratio for, let's see, 4 moles of iron for 2 moles of Fe2O3. And this is going to be 2.16 moles of Fe2O3. How many moles of iron 3 oxide can be produced from 312 moles of oxygen gas? Now, this is a much bigger number than we've been working with, but don't let that scare you. When we started with numbers like 4, we were getting answers of like 2 or 8. When we're starting with numbers of about 300, you can expect answers in the 2, 4, 500 range probably. And so don't let the size of the number scare you. If you do the work right and you put it in your calculator right, you need to trust yourself. So we're comparing moles of oxygen with moles of the product, iron 3 oxide. Coefficient for oxygen is 3. Coefficient for Fe2O3 is 2. And so we are looking at, this comes out to 208 moles of our product. Now we're looking at it differently in the next question. We know that 10.0 moles were produced. We want to know how much iron was used up. So start with things that we know. And the mole ratio here is between moles of iron 3 oxide and moles of iron. You'll notice that the question says what quantity of iron. It doesn't really specify units. And in this situation, since it doesn't specify units, I'm going to leave it in moles, because a mole is a quantity and it didn't tell me otherwise. So we'll just stick with moles and keep it simple. The mole ratio: 2 moles of Fe2O3, 4 moles of iron. And this comes out to 20.0 moles of iron.